Okay, now let's think about the temperature of the Earth in a more realistic way, where we factor in this atmosphere. The fact that there are clouds immediately makes the Earth somewhat colder by reflecting sunlight off, but it's more complicated than that. To think about the temperature of the Earth, we have to think about what wavelengths radiation goes in and what wavelengths radiation goes out. So here is a spectrum ranging from the ultraviolet through to the far infrared wavelengths. So this region here, between about 0.4 and 0.7 nanometers, is what we call visible light. That's what the human eye can see. Ultraviolet down here gives you sunburn, and infrared out here is where most fibre optic communications and television remotes work in, for example. Now the sun is very hot, 5525 Kelvin at the surface, and that means it's a black body radiation which peaks at visible light. So this red line is what the sun is actually emitting, and the solid red area is what actually gets through the Earth's atmosphere and hits the surface. Because the next graph down here shows what the transmission of the Earth's atmosphere is. And you see in the ultraviolet no light gets through, mostly because of the ozone layer, but in visible wavelength most light does get through. And so that's when you sit and enjoy sunlight on a beautiful day, it's mostly this visible radiation here that's causing the heat that you can see. There's a common misconception that infrared radiation is heat radiation. That's not true. Any electromagnetic radiation carries energy, and most of the heat is visible light, though a bit of it's in the infrared. So that's the heat coming in, and most of it gets through. How about the heat going out? Well, the Earth is much colder than the Sun. So we've got lines for 210 to 310 Kelvin, so depending whether it's the North Pole or the equator on a hot day. And you can see that they peak in the mid-infrared at wavelengths of around 10 micrometers. But if you look at the transmission, you see that most of the mid-infrared cannot escape. It's blocked. There are particular windows particular wavelengths where you can see through the Earth's atmosphere. As an astronomer, we use these wavelengths to study things. I've spent a lot of my career working in the K-band window, which is this atmospheric window over here. But most is blocked, and it's blocked by different chemicals. So how does a chemical block infrared light? Well, here's my simple model of a carbon dioxide molecule. So it's got the carbon and the 2 oxygen, and because of the chemical bonds, which I've shown as springs here, these are slightly charged. There might be a positive charge on the outside or a negative charge in the middle. I don't know the details, I'm not a chemist. But what does happen is, when you apply an electromagnetic wave goes past the carbon dioxide molecule, it has an alternating electric field that goes up, down, up, down, up, down, which is going to be shown by this blue arrow here. And that's going to pull on the oxygen one way and the carbon the other way. So here we've got a simulation where this happens. And what you can see is not very much happening. So most frequencies of electromagnetic wave don't have much effect. But if we change the frequency, we'll see we've got a much higher frequency here, and now we are getting motion. We've got the oxygen and the carbon going in opposite directions. What's happening here is we've got a resonant frequency, a frequency that matches the natural vibration of the carbon dioxide in this particular way. And so because there's a resonance, the incoming electromagnetic wave excites the carbon dioxide, which therefore scatters or absorbs the radiation. Here's another frequency that also resonates. There's more than one way carbon dioxide can resonate. Previously we saw them all moving in a line. Now they're moving in opposite directions, so the carbon goes up and the oxygen goes down and vice versa. And once again it's resonant, and that means that this particular frequency, this particular wavelength, will cause absorption. So there are basically three ways that the carbon dioxide can vibrate. There's vibration in a line with the oxygen and carbon moving in opposite directions, vibration in a line where the oxygen moves in and out while the carbon remains still. That's the first one we saw. And a third one where the oxygen atoms move up and down like a bird flapping its wings. That's the last one we saw. So you've got moving like this, moving like this, and moving like this. All sorts of dance moves. Now, we've got the asymmetric stretch mode here. That's the one where they go like this. But the crucial one is this absorption here. So that's the wavelength where you get the asymmetric stretch mode. And this absorption is the bending mode. That's this one going up and down. And this is the one that causes global warming. It's called the bending mode, and that's the one that's causing so much trouble around the world at the moment. Now, that's a somewhat oversimplification. To understand these absorption properly, you need quantum mechanics. You have an energy diagram with the different modes. So the energy levels of the bending mode are the ones jumping between them is what causes problems, and the energy in this mode is quantized. And if you look at this absorption in great detail, here, for example, is the edge of this bending mode, and you zoom in on it, you see the absorption or transmission is actually a very complicated pattern. And this is complicated quantum mechanics. Anyone who's done molecular spectroscopy or atomic physics will know something about this, but there are multiple modes of quantum states and vibrations all going together. So it's a bit more complicated than the pure classical electromagnetic up and down motion, but that gives you a basic idea of what's going on here. So what's happening? All these absorption are caused by different molecules, water vapor, carbon dioxide and so on, with particular vibration modes which block particular wavelengths, and that stops some of the radiation going through. An interesting thing, of course, you see carbon dioxide, you got basically the absorption down here, but look at water vapor. Water is absorbing all over the place. It's a far stronger absorber in the infrared than carbon dioxide. And why is that the case? Well, here's my simple simulation of water. H2O, so what's going on here? Two hydrogen, the oxygen in the middle. Because this molecule, things are not in a line, there are many more ways it can vibrate. Here we've got a totally classical model, and of course in quantum mechanics it's even more complicated, but basically you get more ways to vibrate. You've got rotation around different axes. It looks like some sort of drunken boxer going on here. And because there are so many more ways it can vibrate, and the multiplications of these, so you can have rotation around one axis plus spinning plus vibrating in and out all at the same time, you get a whole bunch of absorption which completely covers the spectrum. And in fact, water vapor is totally crucial to life on Earth. Here's a quote from a 19th century or so, over 140 years ago, scientist. "Water vapour is a blanket more necessary to the vegetable life of England than clothing is to man. Remove for a single summer night the aqueous vapour from the air, and the sun would rise upon an island held fast in the iron grip of frost."